Okay. Welcome back, everyone. I hope that it was that you enjoyed the previous talk, and that also that you made use of the small coffee break. What we'll do next is we will have our student showcase. Some of these guys are finishing their projects and looking for internships, but we will start with two recent graduates that are already in industry. They've moved to Copenhagen. The way that we will do this is slightly different than the talks because the time is short for them. So each talk should run around 6 to 7 minutes, something like that, and we will do the Q&A at the very end, instead of after every talk, so that we keep the flow going. So first, it's Descent Raytraced, which is a project from I think 2 years ago. Guys, the floor is yours.
All right. Hello, everyone. Yeah, as Bojan already said, we are currently no longer studying here. We graduated this summer, but yeah, we now work at Playdead. But before we actually start the presentation, has anybody heard of this Descent Raytraced before? Yeah, okay, that's about what I expected. I mean, the game is pretty old, it's 1995, and it's not that popular, but good to see that some people know it. Also, you guys. Yeah, so we quickly start off with meeting the team. This was the team that we worked with for this whole year project. Obviously very talented team, you know, that's what you usually say. And now we will just have a small little video of the game playing and a path trace version. So yeah, as you can see, the lava is really lighting up the room here, it gives a really nice red glow. There's a lot of lasers and fighting and shooting going on in this game, so it lends itself really well to path tracing. Also don't mind the flying skills there. And now we will show you the exact same sequence, but in a different view. We will show you the specular lighting that is coming from that is being rendered here. So everything from the lava, from the lasers, the rockets, the explosions, everything casts light, which makes for a very nice firework effect. Like everything's kind of blowing up in your face. So yeah, that is the very quick showcase, and now we will go into a little bit of detail, but maybe not too much. But Daniel will take over from here.
Yes. So the game is path traced. It's a relatively straightforward implementation. It's a single bounce, and we have reservoir importance sampling for the light sampling. It's not restir, but you know, don't need that for Descent. We have an importance sampled physically based BRDF. We use spatial temporal variance guided filtering for the denoising, and we of course have TAA. We have a flood fill based light culling algorithm, which is quite convenient for how the levels in Descent are laid out as a warped 3D grid. And it's all implemented from scratch in DirectX 12 using DXR. And I will show you here, we have some pretty undersampled lighting. It's pretty nasty. And after we feed it through SVGF, we have a pretty nice result. But because the samples some really sparse fireflies, you will see that there are still a lot of things that SVGF is not catching because it is not properly estimating the variance. And what we found, which is a really nice solution from actually a reblur, is to just basically do TAA on the result and stabilize it. And this makes the end result way nicer, and you can reduce the resampling history for the input into the denoiser, and then rely on neighborhood clamping to have very fast response in this second resampling pass, and that stabilized the result very nicely. That's kind of the only really interesting thing I can highlight from the denoising. Otherwise, you can look at the SVGF paper. And that's what the final lighting will look like. And it's a lot of the artifacts are hidden very nicely by the grimy 8-bit textures.
Yeah, one thing to also mention that's in, I think the history for both diffuse and specular lighting are set to like 4 frames by default. So yeah, it's really reactive in our game, so you don't really see that much ghosting. There's still going to be some ghosting depending on your frame rate, of course, but it's really reactive. It's really, really fast. It really adapts very quickly. I just want to quickly talk about performance. We did kind of a wavefront-ish approach, I will call this. We had an Uber shader for a long time, but as you might expect, an Uber shader that just goes into all kinds of different directions and bounces off in all kinds of different directions and then samples all kinds of different materials, that might not be good for performance. Surprise. So what we do instead is is kind of inspired by Quake 2 RTX in some ways. What we first do is we shoot the primary rays and we only determine this for visibility and then filling the G buffers, but we don't do actually any shading there. Then in the second pass, we actually evaluate the direct lighting based on what we have in the G buffers. And then in the third pass, we will do the one indirect bounce, which then also does the shading. And well, step 4, there's not really a pass, but it's profit because the time was like cut down by half for the entire pass here. So yeah, it runs on pretty much any RTX hardware with pretty good performance. We even had some users and the developer of ours run this on the GTX 1060. Now, you might be surprised to see a GTX 1060 here, but apparently there's some fallbacks in the drivers sometimes that actually allows you to do ray tracing. At least that's my understanding of it. And we had a user actually report that they got it running on Steam Deck at playable frame rates, so that's pretty cool. And at some point in a later stage, we also added AMD FSR2, so if you want to use upscaling, if you need it, then you can. But yeah, that's it already. So if you want to play the game, there's the link, but you could probably just look for DXX Raytracer on Google and you will have it first thing probably. And if you have questions, you might ask them now, but probably better just approach us during the conference because we will be here all week. So yeah, thank you.
Take that one off and give it to. Okay, thank you very much. That was lovely. I also noticed that they updated the GitHub repository yesterday, so they've been nervous about this talk, I guess. Our next speaker is Stefan. For Stefan, I think this was a side project or a kind of, across multiple years, but mostly in his year 3, and he's already heading out to Malmö to Ubisoft Massive somewhere next month, but we caught him just in time to be able to deliver this.
Thank you very much. No, that direction. Hello everyone, my name is Stefan Pijnacker. I'm currently a 4th-year graphics programmer here at BUAS. I'm currently doing internships, like Bojan told. I am exploring the computer graphics research field over at Reverse Research, and next semester I wanted to try out the AAA field, so I got a chance to get to work on Snowdrop, one of Ubisoft's engine, over at Ubisoft Massive. So my talk, Tackling Graphics, One Dragon at a Time, is kind of my journey so far as a graphics programmer, and I wanted to share that. So we go where all good things begin, which is of course our first Raytracer, and mine was not made in one weekend. But even though it wasn't made in a weekend, I had a lot of fun working on it. I wanted to push it further and further until I pushed it too far. But luckily, after some time, I managed to create cool scenes that at least told me I want to be a graphics programmer. So this was my first year, and then we skip over to my next year, and 2 renderers and a game engine project later, I asked myself, what did I learn? And I realized that my foundation wasn't really good. I realized that just because I added the technique, it didn't mean that I actually knew it. I never took the time to ask why things were the way they were. What is the rendering equation? Why is the rendering equation it is? And at the start of my 3rd year, I wanted to challenge my understanding by redoing some projects instead of doing new ones. And my personal guidelines were, I had to start with the fundamentals. I could only implement things if I understood it, and avoid making the it-can-do-everything engine that I would never finish. So I asked myself, do I actually understand light transport? And to my surprise, I didn't. So I might not know it by heart after all. But after a few more days, I realized that I still didn't. But I stuck with it, I read the papers, and suddenly I started matching my ground truth, which was quite fun. Surprisingly, I learned a lot more than I thought. By asking why things work the way they work, I suddenly understood materials, I understood the mathematics behind it, and that carried out through my next project. I learned, hey, I can learn this stuff. Do I know the fundamental rasterization techniques? And it went off quite well, and then I started learning the GLTF file formats, and luckily, after a few more days, it worked out. And in the end, I started noticing something, that a lot of stuff suddenly clicked faster because I knew why materials work the way they work. PBR was suddenly quite easy to implement. I understood it. And by redoing my project, CPU to GPU synchronization work, the resource system, the binding of layout, and I ended up learning a bunch of things. So then my next question was, hey, I never did compute shaders, but those are fundamental for graphics as well. Can I understand it better? And to my surprise, it actually went quite smoothly. Once I had a compute shader running, the rest was quite easy. And I wanted to do something quite more complex than a bunch of particles moving. I wanted to do M-body, which is quite expensive. And that's when I encountered the beautiful worlds of infinite and not a number. I was stuck with 1 or 2 days for that, and then suddenly I discovered the issue, and I managed to create M-body particle simulation. And it was really fun for me, it was interactive and stuff, and I wanted to do more particle simulation. If everyone has a fear of holes, please close your eyes. I did Physarum folicephalum, which is a slime mold simulation with 5 or 10 million particles running. And afterwards I did something called particle life, which is a sort of simulation how cells might react with each other. Based on their color, they either get attracted or repelled by other particles. And suddenly at this simulations with just a bunch of input parameters. And that was really fun to me. And it was a great way for me to learn compute shaders. And another notable thing was that every DirectX 12 compute shader tutorial already assumed that you did a bunch of compute shaders, which I didn't. So I ended up writing articles about it, which was a really fun experience, and also a side of graphics that I haven't done before. Then lastly, at the end of my 3rd year, I asked myself, is there a way to combine it all? And then my lecturer, Jacco Bicker, wouldn't stop about talking about ray tracing. So I ended up deciding doing DXR, hardware accelerated ray tracing. And this was sort of like a cool combination of the stuff that I learned. I couldn't have done it if I didn't do DirectX 12 projects. I couldn't have done it if I did the path tracer. And then after working on it for some more, I managed to get renders I was quite satisfied with. Something 2 years ago I would have never been able to do. So my conclusion, and this mainly here for the younger audience that is still learning graphics, question your understanding sometimes. Chances are high you learn a lot more than you think. Ask why. It can be really fun to learn why materials react the way they work. I couldn't stop looking at my walls, and my girlfriend was wondering if I was going insane, but I was trying to see how the light reacted. And consider redoing projects. I already had a ray trace in my portfolio. I don't need a new one, right? Well, clearly the bottom one is more interesting to look at. So that was basically my journey so far as a graphics programmer. I'm hoping to see where it can go next. I hope it was fun listening, and thanks for the time.
Thank you very much, Stefan. Our next one is Angel. This was for them as well a year 3 project and ray tracing as well.
All right. Hello, everyone. I am Angel Angelov, as you can see. I'm one of the 3 graphics programmers behind the On the Bubble project, and I'll get to that shortly. Currently doing an internship in Triumph Studios. Anyway, let's get to and I'll be talking to you about path tracing in our On the Bubble project. So what is On the Bubble? It's a game. That's what we do here. We make games. But more specifically, it's a physics-based platformer game. It's made in a fully custom engine throughout our year 3. We start in September for it, and then we do a block of research, and then we continue for the entire year. We start with 7 people. And we ended up being a 13-person project, and it was mostly programmers, as you can imagine. It's a game that works both on Windows and PlayStation 5, which was part of our brief. So we had to do that, and it had to be also available on Steam. So Now, more specifically about the rendering, what are some of the interesting design decisions we did early on? So we did not want to do with any rasterization because that would have cost time wrapping over Windows and PlayStation. So we decided to add support only for DXR and compute. So that is all the rendering we do. Well, there's an asterisk. We do debug lines, but only on Windows, and they're rasterized, but that's it. We also decided to do, we heard that bindlessly doing resources is the new cool thing now. So that's what we also did. All of our models are set up bindlessly. And since it's a path tracer, all of our light comes from the skybox and the emissive triangles that are in the scene. So no point lights, no specific objects that are just lights. We also did away with vertex animation, only transform animations, and we are also doing only inline ray tracing, since again, wrapping the stuff over shader binding tables was something we didn't want to deal with. We decided to spend our time somewhere else. And we also, since it had to run both on Windows and PlayStation, we had one person create a shader transpiler which converted all of the HLSR shaders to the PlayStation 5 format. So it was basically code gen. Don't do code gen. This is the render loop. Obviously starts with begin frame, ends with end frame. Our first step in it is to update the bindless heap, which is all of our models, as I said before, and the way that you access them. Then we do TLAS related stuff, like create at every frame. We did some profiling. Creating at every frame was faster because we do a lot of tracing, obviously. Our performance there. Then comes the actual wavefront path tracing loop. We start with our primary rays, which are generated from the camera. And then we get into the actual meat of the loop, which is these 4 shaders. The extend shader takes that bunch of rays, queries it against the geometry, and moves on. Then comes the shade shader, which is our big Uber shader. It stochastically determines all of the materials. And yeah, then we do direct illumination, which is our, for direct illumination, we do restir on the first bounce because we would, restir DI. We couldn't get restir PT to work because it's a bit more complex math-wise. Yeah, then in the connect stage, we evaluate those shadow rays that come from our direct illumination. And obviously, that happens in a loop. And our loop consisted of 5 bounces. Then we get to finalize, which collects all of this data, puts it in one color texture. We move on to the reprojection, which allows us to temporally reuse the data. Oh, what did I do? Oh, okay. Then we do denoising, which is actually 3 shaders, not 1. But this, for which we also, like the descent team, use SVGF. Then comes some quality of life shaders like the outline and the grid shader, which are there for our editor, since we can we have a level editor and we can share levels. And creating levels is easier with those. Then the post-processing, which we added bloom and tone mapping. And finally, the UI. For the UI, we used a library called Ultralight, which was really nice because it allowed us that all of our UI can be written like as HTML. That's what Ultralight does. And that runs both on Windows and PlayStation 5. Actually, finding HTML programmers was a bit difficult. This is the output image of our accumulated path tracer, which is another state of the render we had. This was our ground truth if you let it accumulate for as long as possible. This one is based on Blender's, I think, material evaluation. But this is actually not real time. This is if you give it as much time as possible. This is a scene all of you are familiar with. It's Bistro, I hope at least. And this is how it looks like in our path tracer. And a friend of mine that also worked on this project wanted me to include this because it's a cool showcase of the class. And I also agree with him that it's cool. Anyway, this was it for my part of GPC. I hope if you have any questions, yeah, hit us up afterwards.
Okay, thank you, Angel. Next is Raresh, and he will show his year 2 project actually. So we are kind of going back towards through the years. So starting from alumni and going slowly to show what our students are doing in their second year.
As a graphics enthusiast, I've always been fascinated about how light is calculated in video games. I know we're all here excited about path tracing, ray tracing, or newer additions such as Radiance Cascades. But today, I will showcase you how I approached the topic of global illumination in an interesting manner last year as a stretch goal during our Block C project. My name is Raresh Dumitru. I'm a year 3 project student here at BUAS, and this is noise-free global illumination approach with cone tracing and server automata. First of all, we need a special way of representing our scene. I must say that the whole project was developed inside the voxel game engine. However, this technique can be theoretically applied in any other regular renderers at the expense and effort of voxelizing the scene in real time. In this example, the world is represented by a 3D texture on the GPU with the size of 256 cubed with the format of RGBA. In the alpha channel, as you can see there, we store our occupancy information, 0 being empty or 1 being filled with a solid voxel. The RGB channels are reserved to store lighting information that will be useful later. Now, for those who don't know, server automata is a simple algorithm where a grid of cells evolves over time according to rules based on the states of neighboring cells. Now, I choose to use this approach to propagate our direct lighting into our scene for a few reasons. It's fast since it propagates one step at a time. It doesn't care about how many lights we place in the scene. It results in an interesting stylized effect with a slow propagating light. The effect is achieved by this simple formula behind me, where each cell holds a little less light than the neighbors. Of course, this means that the light propagated is just an approximation and no way near realistic lighting, but maybe realism is not everything we aim for anyway. Here you can see how light is being propagated in real time using server automata. The results were blocky and not that impressive, to be honest. Now let's talk a little bit about cone tracing, the method that will bring life to our blocky mess. Cone tracing is an idea proposed by NVIDIA back in 2013, where we could replace the rays with cones for a noise-free approximation of light bounce in our world. The cones work by sampling values at the different map levels based on the distance traversed. This means we do need to make 3D map maps of our 3D texture, but that was easily achieved with another quick compute shaders. My implementation consists of 1 volumetric cone that traverses the initial ray direction from the camera, 5 diffuse cones to simulate the one bounce into our scene, and 1 specular cone, all of them making good use of our light data that has been propagated earlier by server automata. I start by shooting 5 cones out back to the scene, trying to cover as much as I can while accumulating the light information. The average result is the approximated 1 bounce information that we need for that sweet global illumination effect. This also gets rid of the per voxel look we had earlier with the server automata and yields a subtle ambient occlusion effect for free, as you can see in this comparison shot. For shadows, I use 1 cone from the heat location towards the light source. This means I sample voxel occupancy instead of color this time, and the result will be a value between 0 and 1 depending on how much occupied space we traverse. This results in soft dynamic shadows by barely writing any new code. Here is what the progress looks like right now, with the world casting soft shadows that blend together on the ground. But why stop here when we can still sample data? To approximate specular reflection, I cast an additional cone from the heat position, reflecting it based on the camera view direction and normal. Here is the result in action in a scene where all the voxels have the same specularity. For volumetric effects, I shoot a cone along the camera view direction to sample the direct light that is in front of us. I then add this on top of the other effects for a final image. As you can see, the volumetric effect plays along nicely with Server Automata, resulting in this charming slow expansion of the light volume. In the end, here is a side-by-side comparison between how I started with a blocky mesh results from Server Automata and the final renders polished with all the enhanced effects. Thank you all so much for your time. Behind me you have my contacts if you want to reach out to me, and feel free to ask any questions at the end. Hope you enjoy the rest of the talks.
Thank you. Next is Carolina.
Hello, everyone. My name is, one moment, yes. My name is Carolina, and I'm currently a third-year student here at BUAS. And today I will be presenting the renderer I worked on last year together with a fellow student, Marcin. Unfortunately, he was not able to join me here today, so I have made sure to add his contact information on the last slide. So let's start with some general information about Coral Engine. Coral Engine is a custom tech project I worked with about 8 more people for 4 months. And the main goal of it was to create an engine that would support creating top-down RPG games. And this, of course, inspired a lot of the features that we added to the engine together with Marcin. The engine is multi-platform. It supports PS5 and PC. I was personally responsible for the PC-specific code, while Marcin worked on PS5. So let's see what goes into rendering a frame in Coral Engine. First, we start by setting up instancing. Then we do a shadow map pass, depth 3 pass, followed by clustering lights. Then opaque and transparent geometry passes, post-processing, and finally UI. For instancing, we knew our scenes would be very dense. First of all, they're procedurally generated and have a lot of repeating meshes. We also have a lot of enemies, especially in endgame, and they leave dead bodies behind, so it will accumulate very fast. And of course, we also have particles. For this reason, instancing was very important for us. And the way we did it was by, first of all, sorting the entities in the ECS based on the mesh and material pairs. And then we divided the rendering data we needed into 4 separate buffers, one for each pass that we did. So for example, the outlines, the depth pass, the shadows, and also the shading. And that meant that some data would be repeated in memory, but that's risk we took for better memory locality. Next, we get to the depth pass. Our depth 3 pass generates 2 depth maps. The top one is used for optimizing away clusters, and as well as avoiding overdraw. And the second one is used during post-processing for the outlines of the meshes. Now we get to light clustering. This is a method that we use to render tens of thousands of lights. And we do this by, first of all, subdividing the viewing frustum into axis-aligned bounding boxes. Then we call away these boxes if they are inactive, aka if they don't have meshes inside of them. And finally, we assign the point lights to the boxes depending on the area they affect. To actually use the lights during the shading pass, we simply index into the viewing frustum structure and get the lights that we need. For the opaque and transparent passes, here's where everything comes together. In terms of the transparent pass, we only use it for the particles since we were on a bit of a time crunch. As a shading model, we use PBR for the most part. During a last-minute decision, we did decide to scratch that and use a simple diffuse shader instead, since PBR was a bottleneck for us, and well, we just didn't see that much of a difference between the two because of the assets that we used. Then we applied the shadow map using PCF for sampling, and here fog is as well computed. As you saw in the trailer, we have some post-processing effects. We support HDR as well as exposure tweaking. We support LUTs, outlines, and as well screen space ambient occlusion. And finally, we have UI. Our UI system is actually pretty simple. We support sprites and we also support font rendering. For font rendering, we use a STB2 TrueType, which generates a sprite sheet out of a TTF file. And then we use the provided functions to sample the right symbols that we need. And yes, that will be everything. Thank you for your attention.
Thank you, Carolina. To put it a bit into perspective, this is also a year two project, and it was developed. The game was developed over time of between 2 and 3 months. So it's not a lot of dev time to create a lot of these effects and art and everything that goes into it. Next we have Max.
Thank you. That is not right. That is not me. I think the order is wrong. Okay. Maybe I need a...
Okay, then we'll bring Ferry, another who is right now in year 3, and he will also show his year 2 project from last year.
All right, thanks. All right, good morning, everyone. My name is Ferry, and I'll be giving a presentation on the Blossom engine that I worked on last year as a graphics programmer. This was a student project where we created a game engine inspired by a game called Flower. I was a graphics programmer on the team and was mainly concerned with rendering the grass that you see throughout the landscapes. And today I want to showcase the techniques relating to the grass and how it all came together. The grass rendering in Blossom is what pulls the scene together and gives it overgrown and nature feeling to it. But to accomplish this, it requires a lot of triangles and processing to make it feel dense and animated. In the following slides, we'll be touching on how I optimized the performance and how I made it viable for a large landscape, but also how I made sure that the grass blades could be animated and affected by both wind and objects moving through the scene. The first thing to realize is that all this grass poses a huge amount of triangles, and in the following slides I talk about the optimization techniques that we use, starting with this one, instancing. Each grass blade at its core is just a rectangle, and as such we can instance it throughout the scene without performing individual draw calls. During the vertex shader step we can change the shape of this rectangle to match that of a grass blade. Making use of a curve, we can change the rectangle into a shape that matches a grass blade. Since we just have a rectangle as well, we can also use a triangle strip topology to make it a little bit more optimized, especially with the sheer amount of vertices that are in the scene. With this in mind, we can instance all the grass blades at once and be smart about how many draw calls we use. I organize all the grass that's in the scene into chunks so we can perform different kinds of optimization techniques. Each chunk can be affected separately by the different techniques, like different levels of detail, culling, and another approach I use is to sort the chunks based on distance from the camera so we reduce the amount of overdraw. By grouping the grass blades into chunks, we can perform a coarse culling algorithm on the CPU. We can easily test the ABB of the chunk with the frustum and remove all the chunks that aren't in the screen. Since the chunks are coarse, we are dealing with a small amount of them on the CPU and can easily receive big gains for minimal cost. The next optimization technique is about decreasing the level of detail based on the distance from the camera. The further away the camera is, the more we lower the amount of triangles on the grass blades. However, we still need at least 4 triangles to be able to bend it and have some kind of animation, which is still pretty intensive for large scenes. So the next thing I implemented was making the grass render only having the positions interleaved in the buffer, so that if we only render a quarter of them, we still remain with a dense field. We can then scale up the grass blades to make it look like it's covering a similar density. This can be a noticeable effect, but due to the depth of field effect we have in the game and the angle of the player's camera, this is hidden well enough that we can get away with it. The video isn't working. Oh well. To be some... There we go. To breathe some life into the scene, we try to emulate a wind over all the grass blades. By scrolling a Perlin noise texture and sampling it by using the world position of the grass blade, we can create a simple force that can be used as an input for the bending effect. This results in an effect that looks like wind blowing over the landscape. We also have control over the wind direction, strength, and speed, allowing us to customize how we want our wind to look in our scene. Yeah, there are videos, but they aren't loading, so I'm sorry. The displacement effect is what makes the scene feels interactive while you're moving through it as a player. While you're moving, the grass moves out of the way, and the environment responds to your actions. This effect is achieved by writing the velocity of the player into the texture that is sampled by the grass when it gets animated. Yeah, the presentation isn't.
Second one.
Yes. No. They don't load. Yeah, that skips to the next one. Oh well, I'm sorry for the technical difficulties. The videos aren't loading. Yeah, I'll finish the presentation. So yeah, the final effect we have is a displacement effect that when the player is moving, the grass blades move out of the way while you're moving around. This gives that interactive feeling to the landscape, since you can actually see the grass responding to your actions as a player. And it's implemented by using a displacement field where we write the velocity of the player into a displacement map that then during the animation cycle can be read from by the grass, and the grass blades can be moved out of the way. All these effects come together in the final product. Yeah, here, unfortunately the video isn't working. But we can see all the optimization effects being used to make the game feel real time. So we have instancing, LODing, and culling. Then you can see the various animation for the wind and the player to make the grass feel alive and responsive. There's still many different approaches to try and ways to optimize this. Recently I've been thinking about using a GPU-driven pipeline to perform LODing and culling on a GPU instead to make it even faster. I also think there's still improvements to make in how we blend between the different LODs to make it look like a nicer scene with less hard edges. Thank you for listening to my presentation. If you want to find me or reach out, you can do so through these socials. I'm currently working on a year-long project to produce a game for the Steam Deck using Vulkan. If you would like to come chat with me about this or anything else, please come up to me. And if you want to see the actual videos, I can also show those. So, thanks everyone.
Maybe we can play this one. I was refusing. Nope. Did you test if it was working on its own? While you present. While you present. You just try present.
Radiance Cascades.
Yeah. Does this one work? Just click here. Or this one now. All right, this time for real. Hello everyone. I'm Max and I'm a second-year student here at BUAS, and I'm going to be giving you a brief showcase of an efficient representation of radiance fields called Radiance Cascades, which was also mentioned earlier. Before I start, I do want to note that I had to shorten the explanations a lot because it's a short talk. So if you're feeling that stuff is missing, that's probably true. So don't worry though, because at the end I have a list of some great resources for you to check out if you want to learn more. So let's get started. So first of all, what is a radiance field? It is simply a way to represent the incoming light for any direction at any point within some area. The area usually being your scene or your screen in 2D. And a naive approach to doing that might be to place evenly spaced out probes across that area and shoot out uniform rays in all directions. So of course has some issues, For example, the angular aliasing far away that you might experience, because the physical distance between the rays grows the further away you get from the origin of the probe. And of course, there's the massive memory requirement that this would have. As you can imagine, you would need a lot of those probes and a lot of rays not to miss objects. So let's make two key observations that undermine Radiance Cascades as a whole. The first one is the angular one, which is based on the angular aliasing issue that I just mentioned. Basically, when we are further away from objects, we need more rays to not miss them. And on the right, we see the spatial observation, which basically states that we only really need 2 probes to resolve a penumbra correctly, which you can see as the blue dots there, because everything in between is just a linear interpolation of those 2 values. And those 2 come together in the original paper by Alexander Senikov as the penumbra condition. While the maximum angle between our rays decreases with distance, the maximum distance between probes increases, and vice versa. These are inversely proportional. So, how do we go about exploiting these observations? Well, first of all, we have the problem that classic probes we're all used to can hit objects at virtually any distance in the scene. What we want to do is we want to narrow the possible hit distance window. One way to do this is, as we see on the left here, by splitting our classic probes into rings. Not only does this narrow that hit distance window, it also allows us to change the parameters for each of those rings, which we can see on the right there, where we are decreasing the angle between the rays with each subsequent ring. And these new rays with a fixed length are referred to as intervals in the context of Radiance Cascades. And we can also see on the right there that now, because we are decreasing that angle as we go out, the physical distance at the edge of the rings between the rays stays relatively stable, basically solving that angular aliasing issue far away that we had. But this doesn't yet solve our memory requirement issues, because now you might imagine that even the memory requirement has gone up because we now have all these rings. So, if we recall, during the spatial observation, we saw that when we are resolving objects that are farther away, we can increase the spacing between our probes. And to increase the spacing at farther distances, let's use a quad tree-like structure, where each 2x2 block of rings in the illustration on the left here becomes one ring in the illustration on the right. These grids of rings are what we refer to as cascades. They can simply be described as a uniform grid of rings where all rings have equal properties. In the case of the illustrations presented here, using the quad tree-like structure, 16 blue intervals would become 8 green intervals, effectively halving the memory cost per cascade. This means that the total memory usage of all cascades together would approach 2x the memory used by the first cascade. And the way that the total memory usage scales with the number of cascades depends on the branch factor. And in this case, there is a branch factor of 2x, 2x, which means that the spacing of probes increases by 2x on each axis, so 4x in total in 2D. And the angle between the rays decreases by 2x. Another common branch factor is 2x, 4x, in which case the memory used by each cascade is the same as the previous one, meaning the memory usage would grow linearly with the number of cascades. This will effectively solve our memory requirement issue that we saw with the naive approach, where now we have a much more reasonable memory requirement. And this is my implementation in 2D of Radiance Cascades. So it turns out that the representation is so efficient that we can actually compute all of the rays or intervals necessary for it, for such a radiance field, in real time with ray tracing. And that's exactly what's happening here. And this one is made with OpenCL and C++. And on the right here, we see a pretty interesting effect that I've never seen before in any other ray tracing or anything, where I basically use the Radiance Cascades I interpolate them with some noise to get this paint-like effect. And more recently, I've been trying out 3D with Radiance Cascades, which is a lot more involved, but the effects so far are quite good. And this one is made with Vulkan Compute and C++. The implementation right now supports diffuse lighting, and the method that I used here, we started to call SPWI, which stands for Screen Probes World Intervals, meaning that we distribute all the probes over the screen, but we trace their rays in world space, or intervals. And as promised, I've compiled some great resources for you to check out if you want to learn more, including my own article on the fundamentals of Radiance Cascades, linked at the bottom there. Links to all these resources here can be found at the bottom of my article. I didn't bother putting them in the slide because it won't be here for long. So please check out the article if you want to see all of the resources. I highly recommend you check out all of them. It can be very helpful to get explanations from different perspectives. And of course, if you're interested, you should join the Radiance Cascades Discord server, also linked all the way at the bottom of the article. All right, that's it for my showcase about Radiance Cascades. If you would like to follow my future work on Radiance Cascades, feel free to check out my socials. And if you see me around after the showcase, feel free to come up to me if you want to chat about Radiance Cascades or just graphics in general. Thank you for listening.